This is a problem that has appeared on the internet, and there are quite a few YouTube videos on this, but none of them actually give a proof of the solution. So this is my humble contribution. Here's the problem restated, but for N prisoners. On the internet, it's all to do with 100 prisoners. So let's do it for the general case for N prisoners. This is the situation. You've got N prisoners with N even, and these prisoners are numbered from 1 to N, and they're in a jail. The N empty boxes numbered from 1 to N. Then the numbers from 1 to N are permuted, so they're shuffled around. The number is written on a card, and the card is placed in each box. Say, for example, this is the situation in box 1. A card with number 5 is placed in that box, and similarly in box 2, a card with number 1 is put in the box, and the boxes are all sealed. Then each prisoner is allowed to go and open half of the boxes sequentially. So he chooses a box, looks inside, and if the number inside the box matches his number, then he wins. Otherwise, he's allowed to carry on sequentially until he's opened half the boxes. So each prisoner goes in, sequentially opens half the boxes. If in that process his number appears, he's won. If all of the prisoners win, then they're allowed to go free. But if one prisoner loses, so he takes more than half the number of boxes to find his number, then the group loses, the whole group loses. At the end of the whole sequence, then when the prisoner goes in, he opens his N over 2 boxes, maximum of N over 2 boxes. He reseals each box with the card in it, and he exits without communicating to any of the other prisoners. They're allowed to confer before the whole process, and the idea is to try and develop an optimal strategy for opening the boxes so that it optimizes the probability that they can all go free, so that they all win. So in order to deal with this mathematically, let's introduce some notation. If we've got N prisoners, GWN is the probability of a group win for those N prisoners, whereas GLN is the probability that the group of N loses. For a group win, every prisoner must win. For a group loss, it just requires one of them to lose. So here are boxes numbered from 1 to 10. There are 10 prisoners in this case. The numbers from 1 to 10 are shuffled, and they're put on cards and placed in the boxes. Let's let PK denote the probability that prisoner K wins. Then they all win if 1 wins and 2 wins and 3 wins and so on up to finally and N wins. But they lose if 1 loses or 2 loses or 3 loses or finally N loses. So the probability of a group win with N prisoners is the product of the probabilities that they win. So P1 here is a probability that 1 wins. So for a group win, the probability of the group win is the product of those N probabilities. Whereas for a group loss, it's the sum of the probabilities that they're going to lose. So if P1 is the probability that 1 wins, 1 minus P1 is the probability that 1 loses. In order for a win, 1 must win and 2 must win and 3 must win and so on. So it's the product of the probabilities of a win. Whereas for a loss, 1 must lose or 2 must lose or finally N must lose. So it's the sum of the probabilities of a loss. Let's investigate the situation that the boxes are selected randomly. Every prisoner goes in and selects them randomly. Just recall then, the probability of a group win is the product of the probabilities that they each win. Probability of a group loss is the sum of the probabilities that each loses. There's our situation. Let's have a look what happens when prisoner 2 goes in, and he just chooses randomly. So he chooses box 10, then 8, and box 5. In these three cases, the number in the box didn't match his number. So he's lost here, he's lost here, he's lost here. And he carries on, chooses box 3, still wrong. Finally, box 1 has got a 2 in it, so he wins. Right, now prisoner 1 comes in and he has a go. He chooses box 1, nope. Chooses box 3, 5, 8, 10. In each case, the box did not have his number in it, so 1 loses, and that means that the group loses. So let's compute the probabilities here. Here are the 10 prisoners, and each prisoner is allowed to choose half of the boxes. And he's looking for his own number. So he chooses half of the boxes at random. That means the probability that he will uncover his number is a half. So the probability of a win for each prisoner is a half. So probability that 1 wins is a half. That 2 wins, a half. So the probability that 1 and 2 wins is the product, a quarter. 1 over 2 to the power 2. Probability that 3 wins is a half. So the probability that 1 and 2 and 3 wins is the product, 1 over 8, and so on. Probability of a half, a half, a half, 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 half. So the probability that all 10 win, the probability of a group win with n of the prisoners, is the product of all of those, which is 1 over 2 to the n. In this case, the n is 10, so the probability of a group win is 1 over 2 to the 10. 2 to the 10 is 1 over 2, 4, so it's approximately 1 chance in 1,000 of winning. Now there's another strategy which they could adopt, and I'm going to call this the referred box strategy. Prisoner K goes in, and he must first go to the box which bears his number. So prisoner K selects box K and he looks inside. Let's let the number inside box K be BK. If that BK actually matches his number, then he can stop his 1. Otherwise, that number refers him to another box. So the number inside box K is calling it BK. He then goes and opens box BK and looks inside that. So let's call that B or BK. This for short, let's call it B2K. And if that matches his number, then stop, because he's then 1. Otherwise, go to the box referred to in that one and continue in this process. So we just define, just for notation, we define this inductively. BM, and for prisoner N, is the box inside the previous one, BM minus 1. We carry on with this until he either finds his number or the number M exceeds the allowable numbers. So you carry on until you uncover your number, in which case you get a win, or the number of box openings exceeds half the total number of boxes. Just as an example, say we're dealing with prisoner 2. So here's prisoner 2. He goes then straight away to box 2, and he opens that. Inside he sees the number 5, so there's 5 inside box 2. So he has not won on this instance, but he gets a number, 5. So he then goes to box 5, and he looks inside, and there is a number, 4. So he then goes to box 4. He looks inside, there's a number, 1. He then goes to box 1, and he looks inside. There's a number 2, and then he has 1. So it keeps on opening until his number is revealed. It will eventually be revealed, but he only wins if the number of box openings does not exceed half the total number of boxes. Let's just go over that example in a slightly different form. That prisoner 2 going in generated a sequence of box openings. 2 went in and opened box 2, then box 5, 4, 1, and he stopped there because in box 1 was the number 2. So let's call that sequence a cycle. It's a permutation. It's a permutation of the numbers 1 to 10. That is, it's a function from numbers 1 to 10 to the numbers 1 to 10. So these are the inputs, the numbers of the boxes, and these are the numbers associated with that. When 2 went in, prisoner 2 went in, he opened box 2 and saw there the number 5. So he went to box 5 and saw the number 4, went to box 4 and saw the number 1, and he went to box 1 and saw the number 2. The other boxes, 6, 7, 8, 9, 10, and 3, nothing happened with them. So associated with 3 is 3. That was just fixed. So there's our cycle. It's a function from numbers 1 to 10 to the numbers 1 to 10, and it reveals the cycle of choices that he went through in order to finally uncover his number 2 in box 1. So with this referred box strategy, what is being generated is a sequence, a cycle of length m. Prisoner K goes to box K, he looks inside and he sees the number BK, and then he goes to that box and so on. And say this is then the cycle that has been generated with m objects in it. The list has got m objects in it, so he generates a cycle of length m, say. What we need to do is find the number of permutations of n things which contain an m cycle. Now, just a primer on counting lists. So we've got n different objects and we've got to choose m of them, and we've got to choose them sequentially. A first one and then a second and so on. So x1 is the first choice, x2 is the second, and the position in the list is the order in which it was selected. So x1 first, then x2, and finally xm. Now this can be any objects, but if they're all different objects, you might as well just number them from 1 to n, and without any loss of generality, we're dealing with the numbers from 1 to n. So we are choosing numbers from the set of numbers 1 to n. And we're assuming here that once an object is chosen, it can't be chosen again. So it's chosen without repetition. The objects are chosen without repetition. So we're generating a list of length m by choosing numbers from the numbers 1 to n. So there are n choices for the first. Now you can't choose that one again. So there are n minus 1 choices for the second, n minus 2 choices for the third, and finally n minus m plus 1 choices for the last one. And you're choosing this and that, and finally xm is chosen. And so we're using the product rule. And so the number of ways in which such an m list can be generated is n times n minus 1 times n minus 2, finally times n minus m plus 1. That's the number of ways in which you can form an m list from n things. N choices for the first, n minus 1 for the second, n minus 2 for the third, finally n minus m plus 1 choices for the mth one. That's the number of m lists you can choose from n numbers. Now, again, some elementary combinatorial notation here. For a positive integer n, the factorial of n is denoted by n with an exclamation mark. N factorial is this falling product, n times n minus 1 times n minus 2, right until you hit 1. And for combinatorial reasons, which we won't go into here, we define 0 factorial to be 1. So 4 factorial is 4 times 3 times 2 times 1. That's 24. Now, that was the number of ways in which you can choose m numbers without repetition from n numbers. And there's a cunning way in which we can write this. Let's just carry on with this product here. Let's go down from there. Let's carry on down until we hit a 1. And that means we've added these extra numbers in. And so that is just n factorial over n minus m factorial. So this fall-in product here is n factorial over n minus m factorial. And if that m that we're talking about there is just n itself, so we're choosing n numbers from n numbers, then the number of ways of doing that is n factorial. Of course, choosing the numbers without repetition. So we're selecting n from n without repetition. And the number of ways of doing that is this n factorial. So the number of permutations of n numbers is n factorial. The number of ways of shuffling n objects is n factorial. So the number of ways in which n numbers can be put into n boxes is n factorial. And that distribution is just a function. Let's call it sigma again for a permutation. So sigma 1 refers to the number that goes in box 1. Sigma 2 is the number that goes in box 2, and so on. That sigma is just a function from the numbers 1 to n to the numbers 1 to n, which is 1 to 1 and on to. Every number appears here, and no numbers appear twice. So there are n factorial ways of filling in these numbers here, n factorial ways of putting n numbers into the n boxes. Now, prisoner K starts with box K, and then he carries on to generate a cycle of length m. So he is generating a list of m numbers, and the first, that cycle, let's call it sigma 1. That's a cycle, as we've seen before. And he generates this cycle, and that is part of that permutation. These numbers were permuted by some permutation. The numbers 1 to n were put on cards, shuffled, and put into the boxes. So that was a permutation. He starts choosing. He chooses a box, and he chooses another box, and he chooses another box. That was a cycle, sigma 1, and it was part of a permutation. So his cycle that he generates, sigma 1, is part of the permutation of those n numbers, those n cards that were put into the n boxes. Now the numbers 1 to n were put on cards, they were shuffled, they were permuted, distributed into the boxes by some function, which we're calling sigma. So regarding prisoner K, he goes in and prisoner K goes to box K. He looks inside and he sees the number BK. He opens that box, and so on until he completes his cycle. And then that is a function, and it's composed with another function which permutes the remaining n minus m numbers. So this prisoner K generates a cycle of length m, say. Now, how many ways can that be formed? Well, this K here can be selected in n ways, and the next one can be selected in n minus 1 ways, and so on down the line, till finally the mth one can be selected in n minus m plus 1 ways. And then that means that there's this product, n minus 1 to n minus m plus 1 ways of doing it. And in our factorial notation, that means there's n factorial over n minus m factorial ways of making a cycle of length m from the n numbers. Let us count then the number of permutations of n objects, n numbers, which do have a cycle whose length exceeds the n over 2. Such a permutation looks like this. Sigma is the permutation of the n numbers put onto cards, put in the boxes. Sigma 1 is the cycle of length m, and that m is bigger than n over 2. And sigma 2 is the permutation of the remaining n minus m numbers. So if n were equal to 10, say we've got 10 prisoners, and we're dealing with prisoner 3. So he goes in and does his choice of boxes. He starts then, prisoner 3 starts with box 3. Inside box 3 is the number 4. So he opens that and he sees the number 5. He opens that and sees 6, opens that and sees 8, opens that and sees 7, and when he opens the last one, he sees the 3. So his number has been uncovered. But alas, the cycle has got length 6. And in order to win, that cycle must be 5 or less. So he's exceeded the number of choices, and that means that he has lost. Let's again look at a specific example. We've got our 10 prisoners, 10 numbers. Numbers are put on cards, cards are shuffled, permuted, distributed in the boxes as indicated there. Then prisoner 3 goes in and he chooses first box 3, looks inside box 3, inside he sees the number 4, goes to box 4, inside he sees the number 5, goes to box 5, inside he sees the number 6, generating the cycle. In 6 he sees 8, in box 8 he sees the number 7, he goes to box 7 and uncovers his number 3. So that completes that cycle. Notice that these other numbers here, 1 and 2 and 9 and 10, are not touched. This is a function, and it doesn't alter the numbers 1 and 2 and 9 and 10. The cycle only involved the numbers 3, 4, 5, 6, 7, 8. So that is the cycle that was generated, which is a permutation of the 10 numbers, leaving 1, 2, 9, and 10 fixed, and cycling these numbers in the order that we specified here. Then those remaining numbers, the 1, 2, 9, and 10, they are permuted. In order to get this permutation here, in box 1 there's number 2, in box 2 there's number 1. And similarly up here, in order to get this sigma, this permutation, then inside 9 is 10, and inside 10 is 9. So that's the composition of two little cycles. In box 1 there's 2, in box 2 there's 1, and that closes that cycle. In box 9 there's 10, in box 10 there is the number 9, and that closes it. So the composition of these two functions, the sigma 1 here, the cycle that runs first, which operates only on the numbers 3, 4, 5, 6, 7, 8, and then the next permutation, sigma 2, operates on the remaining numbers, 1 and 2 and 9 and 10. The composition of these two functions, these two permutations, is the original permutation sigma. All permutations can be written as a composition of cycles. So effectively here, this permutation sigma is a composition of this cycle, 1, 2, and the cycle 9, 10. Let's not bother about getting it right down to composition of cycles. It's a composition of two functions, one of which is a cycle. So this was generated by prisoner 3, and the remaining 4 numbers in this case were permuted in the original sigma. So the sigma can be written as a composition of the cycle generated by prisoner 3, composed with a permutation of the remaining 2 objects in this case. Now here's an observation about these cycles. We're going to call 2 cycles sigma I, sigma j equivalent, and we'll use this notation if they represent the same permutation. Now let me try and make that clear. A cycle of length m is equivalent to m minus 1 others. They look different, but they all do the same thing. They all perform the same permutation. Take a look at this cycle here. 1, 3, 2. 1 goes to 3, 3 goes to 2, 2 goes to 1. And this one looks different, but what does it do? 2 goes to 1, 1 goes to 3, 3 goes to 2. It's the same, just starting at a different starting point. They all represent the same permutation of those 3 numbers. So when we're counting cycles, we don't want to count these as different cycles. We want just the one permutation. All three of these cycles represent one permutation. So we're going to count cycles of length m, and they will look different, but they all equivalent. So we'll just count one of them. Every cycle of length m will be in a class, an equivalence class. And we just want to, we will need to count the number of non-equivalent cycles. Our task is to count the number of different cycles of length m, non-equivalent cycles. So let's use capital CM to note the number of cycles of length m for a given permutation. And let's use this little m to be the number of equivalence classes. So as a little picture, here we've got a collection of cycles, calling that capital CM, and there's m cycles per class. All elements in this equivalence class do the same thing. They represent the same permutation. We want to know how many permutations there are, how many essentially different cycles there are. So if there are m of them, m being 6 in this case, and supposing there were 42 total number of cycles is 42, then there'd be 42 over 6, 7 different cycles, non-equivalent cycles. So you count the total number of cycles, including all those which are equivalent to each other, divide by the number per equivalence class, which is m in this case. And that'll give us the total number of different cycles, non-equivalent cycles. So we count the total number of cycles of length m, divide by the number of cycles in each equivalence class, which is m. So we count the total number of cycles, divide by m, and that'll give us the number of different ones, essentially different ones. Now remember, before we established that the number of cycles of length m is n factorial over n minus m factorial. And that included these equivalent cycles. So we divide by m, and this is the number of non-equivalent cycles. Now the observation that we're going to use is that prisoner K loses if he generates a cycle whose length is bigger than half the number of boxes. If he generates a cycle of length m, where that m is bigger than n over 2, then he loses. So putting this all together, if we have a permutation of n numbers, shuffling n numbers, the EM, what we called EM, non-equivalent cycles of length m in that permutation, and there are n minus m factorial permutations of the remaining n minus m numbers. Now we computed this EM as n factorial over n minus m factorial divided by m, and that's the number of permutations which represent a cycle of length m, and the n minus m factorial ways of shuffling the remaining n minus m numbers. So that means it's n factorial over m such permutations which contain a cycle of length m. Now, we're trying to get the probability of the whole group losing, and that is the sum of the individual probabilities of a prisoner losing. And that probability then is the number of cycles of length m with m bigger than n over 2. Remember, if there's a cycle whose length exceeds half the total number of numbers, in other words, if m exceeds n over 2, and there's a cycle of that length, then prisoner m is going to pick it and he's going to lose. So that is the n factorial over m is the number of such permutations which contain a cycle of length m, and then if we add them all up from n over 2 plus 1 to n, that's the total probability that that there will be a cycle of length m, with m being n over 2 plus 1 or bigger. That's the total number of such cycles, and n factorial is the total number of permutations of n things. So if we divide the total number of cycles of length m in the permutation divided by the total number of permutations gives us the probability of that occurring. And these n factorials cancel out. So the probability of a group loss is the sum of these reciprocals. Reciprocals of n over 2 plus 1, n over 2 plus 2, finally 1 over n, because n is n over 2 plus n over 2. So there's n over 2 such elements in this sum. And that is the probability of a group loss for n prisoners. So for a case of 10, then it's the sum of these reciprocals, starting at here n is 10, n over 2 is 5, starting at n over 2 plus 1, which is 6, and up to 10. The sum of those reciprocals is the probability of a group loss with 10 prisoners. Now, if we just use some computational environment, I use MATLAB, there are many such things, Python and so on. Let's just do a little calculation to compute the sum of those reciprocals. So we're taking the sum of the reciprocals of the numbers from 6 to 10, assuming we've got, say, 10 prisoners in this case. Then the probability of a group loss is the sum of the reciprocals of these numbers, which is 0.6456 approximately. And if we now jump up to 100 prisoners, the sum of the reciprocals, starting at 51, going up to 100, is 0.6882. Now we just computed the probability of a group loss. That's that sum of reciprocals. And 1 minus that is the probability of a group win. So for n prisoners, the probability of a group win is 0.35 some change. Probability for 100 prisoners is 0.31 and some change. Now using this rough calculation, the 2 to the power 10, which is 1024, it's approximately 1,000, and that's 10 to the power 3. So if we're dealing with 100 prisoners with the referred box strategy, they have a 31% chance of winning. But if they all choose boxes randomly using this rough approximation here, probability of a group win is 1 over 2 to the 100. Now 2 to the 100 is 2 to the 10 to the 10. 2 to the 10 is 10 to the 3. So that's 1 over 10 to the 30. That's vanishingly small. So just with the right strategy, you can have a probability of a win of 31%, whereas if you do it randomly, the probability is vanishingly small. And this is, it's counterintuitive. That's what all the controversy is about on the internet. And here we are, though. This seems to be true. There hasn't been a proof yet, but a proof can be supplied. Here's a little script, computer program, written in MATLAB code, very similar to Python. And I want to look at these probabilities for increasing n. So I've written a little program to do that. And this is the output of the program. It computes the probability of a win. For n equal to 100, right down to 10, starting with 10, 100, 1,000, and so on. And you can see that these probabilities are converging, it seems, to roughly 0.31, 31%. And if we look at the value of 1 minus the natural log of 2, that's roughly the same thing. So it looks as if these probabilities are converging to 1 minus the natural log of 2 as n increases, as the number of prisoners increases. Can we prove this? Well, yes. Now let's just remind ourselves that we're looking for the probability of a group win. And we can get that from the probability of a group loss for n. prisoners. And we've just seen that the probability of a group loss for n is the sum of the reciprocals of the integers from n over 2 plus 1 to n. Now compare that to that sum of the reciprocals from 1 to n to the area under the function 1 over x from 1 to n. I've shown n equal to 10 here. The sum of the areas under this, sum of the rectangles, 1 over 1 plus 1 over 2 plus 1 over 3, the sum of those areas is approximately the area under this curve. We'll look at some graphics just now to make that a bit clearer. And we want the sum from n over 2 plus 1 to n, not from 1 to n. So with that in mind, the natural log of 10 is the area under this curve, 1 over x, from 1 to 10. Similarly, from 1 to n. What we want is the sum of the reciprocals of the integers from n over 2 plus 1 to n. So that, of course, is the difference between the two. You take the area under the curve 1 over x from 1 to n, 10 in this case, minus the area from 1 to n over 2. And we've got what we want. So this approximates the probability of a group loss. Well, this is the picture for n equal to 10, say. We look at the curve 1 over x from 1 to 10, and the area under that curve is approximated by the sum of the rectangles. And if we want the sum of the rectangles from m over 2 plus 1 to n, then we compute the difference here. And so that is the area under the curve. This is the sum of the rectangles. And if we compute those, you see that the one approximates the other. That, in this case, that's for 10. Well, this is a picture for n equal to 100. And the area under the curve, 0.69 and some change, and the sum of the rectangles, 0.6882. So the one approximates the other. And remember, this is the probability of a loss, a group loss with 100 prisoners. So 1 minus that is a probability of a group win. So what we've shown is that the probability of a group win for n prisoners approaches the number 1 minus the natural log of 2, which is 0.3068 some change. In other words, approximately 31%. That's with the referred box strategy. Whereas the probability of a group win, just choosing randomly, is 1 over 2 to the n. So this probability approaches 1 minus log 2 as n increases. This probability approaches 0 as n increases. Just some thoughts on this. We've shown that the referred box strategy produces a probability of winning of about 31%, whereas if you choose the boxes at random, it becomes vanishingly small as the number of boxes increases. But let's get this clear. Once the numbers have been put on the cards and the cards have been shuffled and placed in the boxes, the die is cast. There's nothing that the prisoners could do about it at this stage. They can't see the numbers in the boxes. So their best chance is to pursue this referred box strategy rather than go randomly. But there's nothing they can do about it at this stage. They have no knowledge of what's in the boxes. So, for example, if this were the way the cards were shuffled, like this, and they say there were only 10, just for typographical reasons, then the die is cast. There's nothing they can do. Number 1 comes in, and number 2 comes in, and 1 opens box. He opens his box, he looks inside, he sees number 2. Then he goes to number 2 and he sees number 1 and he finishes. And the same story for number 2. But when number 3 goes in, he's referred through the cycle of boxes. And that cycle's got length 6, and that's bigger than half the number here. So already, before they even start choosing, 3 is doomed to lose because there's a cycle of length 6. And what about the others? Well, any one of these other prisoners, number 4, 5, 6, 8, and 7, they're going to have the same cycle. If you look at the permutation for number 4, the cycle for number 4, he starts at 4, then he goes through 5, 6, 8, 7, 3, and then in 3, there is his number. And the same for all of them. This is all the same cycle, and it's got length 6, and that dooms them. There's nothing they can do about it. They are destined to lose. But the point is that there are 10 factorial ways in which these cards could be shuffled and put into boxes. And what we have shown is that the probability of a cycle of length 6 or 7 or 8 or 9 or 10 in this case for 10 prisoners is the sum of those reciprocals, 1 over 6 plus 1 over 7 and so on to 1 over 10, and that's around about 0.69. That's the chance of losing. So the prisoners can do nothing about it once those cards are in the boxes. But without the knowledge of what's in the boxes, their best strategy is to pursue this referred box strategy rather than going at random.